Thank you so much for that lovely introduction, David. My only complaint is that you left Vienna off the list of important places. So I've never been, I've never visited Vienna, and that's a great disappointment of mine that I wasn't able to come in person. But I hope in the future that the invitation is still open, because I would love to visit. Okay.
The invitation is still open. It's still open.
Okay, very good. So I tried to set the pace of these lectures so that things are not over. And I'm giving my strongest possible encouragement to the audience to jump in whenever they want and to ask anything they want. Okay, because I think it works best when it takes place as a conversation between me and the audience. So again, strongest encouragement. Whatever you want me to elaborate on, I'm very happy to. Okay, so I was basically instructed that people here know on average a lot about general relativity, Einstein, and geometry, but maybe they know a bit less about, or very little at all about relativistic Euler flow. And possibly you don't know very much at all about some of the recent developments in fluid flow. And by fluid flow, I will mean mostly relativistic Euler flow. But a lot of these results and ideas that I'm going to talk about come from the non-relativistic compressible Euler equations, which have tantalizingly similar structures to what you find in the relativistic case. And so it's almost like you can talk about the two theories at the same time from the perspective of results, of the role that geometry plays, the techniques. You can almost develop the two things in parallel. But I am going to mostly contain the details to the special case of the relativistic Euler equations, because I know that's a particular interest of this audience. Okay, so there are 4 lectures, and let me say a little bit about how I've organized the information and structured the flow of things. And you know, it's not, there's no imperative that we have to get through all the material. So things are so rich and interesting that I'm sort of content to maybe not hit on everything that I could possibly talk about. But if all goes as planned, famous last words, I'm going to start with an introduction to the equations, but with perhaps a more geometric focus than you may have seen in other works. And most of this, let's call it background material, comes from the perspective to us by Dimitrios Christodoulou, with a little bit of new insights imparted coming from works that I've done with Jonathan Luke, Leonardo Abrescia, and Marcelo. We've made some contributions to the geometric insights behind the fluid flow. And there's a lot of applications to the kinds of geometric structures that I'm going to talk about. So I decided to pick one that I thought would be most interesting to this audience. And so I'm going to focus a lot on the relationship between the geometry and the study of shock waves. And I picked shock waves because it's an area of fluid mechanics, both non-relativistic compressible and relativistic. It's an area of fluid mechanics that is undergoing extremely rapid development. And there's been some very interesting things going on. And there's so much to be done in the future. And I thought because this is a school, you would be especially interested in you know, what those open questions are. And central to everything, which will mainly come later and say starting around the 3rd lecture, will be the new formulation of the relativistic Euler equations that I derived with the help from Marcello Descanzi, my collaborator. And this new formulation, which looks a bit crazy the first time you see it, there's no way we would have looked for this beast if we hadn't first seen something similar in the non-relativistic case. And that the non-relativistic work is not something I'm going to focus in detail on in these lectures, but I at least want you to know that the origin for the relativistic stuff is my work with Jonathan Luke on the non-relativistic case. And that in turn was inspired by Chris Adulu's work on irrotational and isentropic relativistic flows. So that comes from his very famous 2007 monograph on the formation of shocks in three-dimensional fluids. And what that book is really about is relativistic fluids in three-dimensional Minkowski space with vanishing vorticity. And then finally, as I already said, more or less, I will talk about applications of the new way of writing the equations. And there will be a special focus on shock waves. But I will mention a few other applications, including applications to low regularity solutions. And it turns out that there's a really deep connection between shock waves and low regularity solutions. And at a high level, it's actually very easy to say what the connection is. The connection is that if you want to prove a low regularity well-posedness result, then secretly what you're trying to do is prevent the instantaneous formation of singularities. You want to rule out the possibility that the solution blows up instantly. That's not the only thing one has to do, of course, but that, secretly that's what you're trying to do at its core. And so far, the only, for most relativistic fluids, the only kind of singularity that we know about is a shock, which is basically a gradient catastrophe, whereas the fluid itself remains bounded. But when you're trying to prove a low regularity result, among the many things you're trying to do is rule out the instantaneous formation of shock waves. So it's kind of like a dual problem to understanding shocks. Like if you want to prove that shocks form, that's one problem. And if you want to show that they don't form for short times under whatever assumptions you're trying to make, that's kind of like the companion problem. And the techniques are very much overlapping. Okay, so much for introductions. Now comes a brief sort of overview meant to communicate the idea that there's a million ways to write the equations without even telling you what relativistic Euler is yet. It's already important for you to know that there's so many ways to write the equations, and there's no universal, to my knowledge, there's no universal way to write them that does everything you need it to do. And so let me just hint at a few of these ways of writing the equations. So the first is as a divergence form, first order quasi-linear hyperbolic PDE system. So here the key is divergence form. And this way is particularly important if you are interested in studying the evolution of solutions that contain shock waves. If you're interested in basically the study of weak solutions, then it's very important to have the divergence form formulation, because ultimately what you want to do is you want to integrate by parts and put all the derivatives onto the test function. And you can do that if you have a divergence form setup. So basically study weak solutions without a divergence form setup. Okay, but that's not really what I'm going to talk about today, because the most interesting version of this problem is not solved yet. That's called the shock development problem. There's been lots of interesting partial progress, but it is still open. Now, if you're just interested in first order quasi-linear hyperbolic, but not necessarily with divergence form, there are lots and lots of ways to do that. And you'll see several today, because this will form these kinds of first order formulations will form the starting point for rewriting the equations in the way that I will need them. If you're interested in irrotational solutions, then you can introduce a fluid potential called phi. Okay, and then as it turns out, so irrotational and isentropic, I'll say more about these words later. It turns out that for such solutions, you can introduce a scalar function called the potential, and then the full dynamics of relativistic Euler is described by a single quasi-linear wave equation of this form. And this D, this connection D, this bold D I'll say more about this later, but this is coming from the space-time metric. This is a D for, so there are going to be multiple space-time connections floating around. In the most sophisticated versions of these problems, you'll have two metrics. You'll have the space-time metric, and then you'll have something called the acoustical metric, which you can think of as the metric of sound waves. Okay, so basically you need to keep track of which connection you're using and how you're raising and lowering indices. And so, this G here is not the space-time G, this is the acoustical metric G. And because there are multiple metrics floating around, that's why I'm writing G inverse. You know, a lot of people in relativity are not used to seeing G inverse written explicitly. And if you work with a problem with just one Lorentzian metric, then there's basically no room for confusion, and you can raise and lower indices. You know, there's only one natural way to do that. But in two-speed or multiple speed problems, you have to be much more careful about how you raise and lower indices, because you have to keep track of which geometry you're interacting with. Okay. You can also introduce so-called Lagrangian coordinates via the flow map of the four velocity, and you can write the relativistic Euler equations using those coordinates. While that's not important for what I'll talk about today, that does become important for the study of what's called the free boundary problem, which is an area which is undergoing a lot of scrutiny from different groups of people. Free boundary problems in fluid mechanics are problems where you have a fluid such that the density vanishes outside of a compact region. So there's really a fluid vacuum boundary. And okay, there's also a liquid. What I just referred to is called a gas. But those problems are very degenerate because the hyperbolic character of the PDEs degenerates when the density goes to 0. And there's a lot of interesting work being done, like I said. Marcello Descanzi and Mihaela Ephraim and Danielle Tataru have a recent local well-posedness result for relativistic Euler for such a gas. But there's a huge number of unsolved problems, and somehow Lagrangian coordinates seem to be really well adapted to that particular setup. Okay. There's another way to write the equations, which are going to be revisited in detail starting around lecture 3. So this is what I mentioned earlier, this new way of writing the equations, which I did with Descanzi, and it was motivated by the non-relativistic work with Jonathan Luke, and also motivated by Christodoulou. And there's a closely related way to thinking about Euler as a wave equation system coupled to a symmetric hyperbolic system that involves an orthonormal frame. And this really nice setup was shown to me by Todd. Actually, I can't see if Todd can be out. There he is. Is that Todd? Yeah. So Todd Oleinik was thinking about different ways of formulating relativistic Euler, and he found this one. And so in this formulation, you introduce an orthonormal frame, and then you also have to control the frame. And finally, so among the most classic ways of writing relativistic Euler, so this is something that works only in 1+1 dimensional symmetry. It could be plane symmetry, it could be spherical symmetry, or some other kind of 1+1 type symmetry. You can rewrite the equations as a quasi-linear transport by introducing the Riemann invariant. So this is the same method that Riemann introduced in the non-relative setting in 1859. And this is a great way for writing the equations for setting up the study of shock waves. And so I'm actually going to focus on this in detail later today, because you can build up incredible amounts of geometric intuition by even in the 1+1 dimensional problem. And the geometry is already very rare. And the variety of phenomena that can be exhibited in 1+1 dimensions is astoundingly rich. You know, I hope to get my hands a little bit dirty with you on this later today even. Okay. So any questions so far? This is just more like a roadmap. Okay. So let me talk about the basic setup of relativistic Euler. So as I mentioned, you can write the equations in divergence form. Okay, but and you need to be careful about which connection you're referring to. So at the beginning, let's take an arbitrary Lorentzian manifold. So you have the manifold M and the space-time metric, which I call H. And on this space-time, okay, if you freeze the space-time and you just study the relativistic Euler flow, then you can write the Euler equations, relativistic Euler equations in divergence form. And I'll say the names of all these variables on the next slide. This T is the energy momentum tensor of the fluid, and I'll display the formula on the next slide as well. And then you have this condition that the length of the forward velocity, u, is always -1, as measured by the space-time metric. And it turns out that this can be thought of as a constraint that is propagated by the flow of other equations. So in other words, if you assume this condition at time 0 or along some space-like Cauchy hypersurface, and then you solve the equations, this constraint will be propagated. Okay, so this is just relativistic Euler with no coupling to Einstein. If you want to couple to Einstein, everybody in this audience probably knows what you have to do. You write down the Einstein field equations, and you put the fluid energy momentum tensor on the right-hand side. Okay, so two big remarks. First of all, the fluid problem is already so rich that I'm going to assume that the space-time, for most of this, the space-time is Minkowski space. So R plus 3 equipped with the Minkowski metric eta. And even though many of the equations will or could be written in a covariant fashion, it will be very convenient for the Greek indices like alpha to explicitly refer to a fixed rectangular coordinate system on the Minkowski space. So, even though, like I said, even though there's like a covariant interpretation you can put on top of everything, it's just very convenient that you should keep in your mind that like the Greek indices are typically referring to these rectangular coordinates. And this becomes important because in a detailed study of the flow, if you're interested in shock waves, multiple coordinate systems become important. And this is tied to geometric optics, in other words, iconal functions, which many of you are familiar with. And in a different setting, if you're trying to understand the details of the maximal development of the initial data, you might need other foliations, which is kind of the same thing as other coordinates. Other foliations adapted to what you expect the boundary of the maximal development to look like. So that's just a little foreshadowing. The second thing I wanted to mention on this slide, which is like already what I consider to be a very interesting open problem, is to understand what version of the story I'm going to present to you today survives when you couple to Einstein equations. So that's like a big unknown in the field, is how, suppose you can understand the fluid geometry and fluid shock waves really well. Can you handle the coupled problem? And if so, how you'll have to understand more than I do right now, the way that these two geometries interact. If you just freeze the space-time, right? If you just like freeze your favorite Lorentzian space-time and say, I want to study the fluid equations on that space-time, then almost everything that I will talk about will carry over to that fixed space-time. However, if you really want to understand the coupled dynamics, that's the problem that's not been understood. Simultaneously studying the evolution of gravity and the fluid, understanding shock waves, and that's not been understood. Okay, so now about these fluid variables. So for a perfect relativistic fluid, here's what the energy momentum tensor looks like. You may have seen this, and again, H is the space-time metric, which for us will typically be Minkowski. And you have all these variables. So you have the forward velocity, the energy density rho, the pressure P, the number density. There's another variable called entropy, which is not explicitly written here. And there's way too many variables and not enough equations until you start adding new things into the theory. So the first thing one adds is something called an equation of states. And actually that's kind of like a loosely worded phrase that means different things to different people. From one perspective, equation of state could be an expression for the density in terms of the density rho in terms of the number density n and the entropy f. At the end of the day, you need this, otherwise you have too many variables and not enough equations to close the system. Now, coming from the laws of thermodynamics, there are other equations and identities So for example, there's an identity that connects rho, p, n, and s. This is one of the laws of thermodynamics, if you want. And then there's a quantity called enthalpy that ends up being important because sort of like one of the cleanest formulations of the equations involves this variable, the enthalpy. And then there's something called temperature. Okay, and all of these things can be computed if you want in terms of the equation of state. Okay, and I'm not going to do the counting for you, but suffice it to say that with all of these relations and the PDEs from the other slide, you basically have enough equations to sort of hope you have unique solutions. There's exactly the right number of equations among all of these things. Okay, but how do you actually think about this in practice? Well, before that, you need some assumptions if you're hoping to have a well-posed theory. Okay, so basically, we're staying away from regions where any of these scalar functions vanish. This is our way of cheaply avoiding vacuum regions. And like I said, the equations are very degenerate, or can be very degenerate at these fluid vacuum boundaries. And there are some thermodynamic assumptions. If some of these quantities, if you express them in terms of n and s and then take their partial derivatives, you have to have something positive. And these inequalities are tied to the laws of thermodynamics. And usually when you try to do estimates for the fluid, it rings loud and clear why you need these things. It's, usually the equations are screaming at you, I'm going to be ill-posed unless this happens. Okay, now what will I mean by equation of state? So one of these positivity conditions, that d rho dn at fixed entropy is positive, that allows you, by implicit function theorem if you want, to solve for n in terms of rho and s. And then you can solve for basically everything in terms of rho and s and the forward velocity. So when I say equation of state, for me, it will mean the pressure as a function of the energy density rho and the entropy s. So this is what I mean by equation of state. And so I will assume that we have a given equation of state that is sufficiently smooth. And once you have once you're calling this the equation of state, you can introduce the most important scalar in this problem, which is the speed of sound. Okay, and it's possibly well known to you from the non-relativistic setting, or this is very well known, that if you take the derivative of the pressure with respect to the density at fixed entropy, you get something called the speed of sound. And this is a very important parameter in the problem for ensuring the well-posedness of the system. And we will assume that the speed of light is positive. And sorry, the speed of sound c is positive and no bigger than 1, where 1 is the speed of light. It turns out I don't think this is fundamental for studying just the fluid itself. This assumption that the speed of sound is no bigger than the speed of light becomes important when you couple to Einstein. But if you're just interested in the fluid, this is not really, as far as I can tell, like fundamental. But C being positive, as I've said, is fundamental. If you want to simplify your life and ignore thermodynamic effects, you can forget about the entropy variable, and as it turns out is kind of equivalent to forgetting about temperature. And you can look at equations of state in which the pressure is a function of rho alone, function of the density alone. Such fluids are called barotropic. They're easier to study for sure. They play an important role in cosmology. In cosmology, you'll see the most famous equations of state are certainly pressure equals constant times rho, or pressure equals rho to a power. But this is a choice to ignore thermodynamics, and you might not always be able to get away with that. So that's it for the fluid itself. You need these kinds of positivity assumptions. But again, if you want to couple the Einstein equations, and you want to ensure that your favorite energy condition is satisfied, for example, if you are looking for a condition, you need other restrictions on the equation of state. So for example, if the density is bigger than or equal to the pressure, you can compute, based on the explicit form of the energy momentum tensor, you can compute that this condition is sufficient for the dominant energy condition in relativity. But we will not need that today. Okay, so about these first order formulations. If you count the number of variables and you count the number of equations, it turns out that the correct number of dynamical quantities, really is, well, depending on how you count, it's either 5 or 6 scalar functions. So basically there are 5, or depending on how you count, 6 scalar functions that uniquely determine everything. And in this way of writing the equations, I'm going to take the pressure, the entropy, and the forward velocity. And so that would be 6 because the forward velocity has 4. This is 6 scalar functions. But like I said earlier, the forward velocity having Minkowski length always -1 is a constraint preserved by the flow. So, one of these forward velocity components is not really dynamic. Okay, so a quick word about raising and lowering indices. Today, when I raise and lower indices, it will be with the Minkowski metric. Okay, so not with this other metric that I plan to introduce in a bit. Okay, so if you take the equations as written on this slide, and you consider their different directions. So you consider the direction. Remember, I'm in Minkowski space, so partial derivatives and covariant derivatives are agreeing. If you take this equation and you project it into the direction parallel to you and the direction that are Minkowski orthogonal to you, and you use all of these thermodynamic relations from the previous slide, you can put the relativistic Euler equations into this form. Okay, so this is like a perfectly good way of setting up the equations in a first order hyperbolic form. And this is like one of the possible starting points for the well-Posedness theory of the equations. Here, this tensor pi is the Minkowski orthogonal projection onto the orthogonal complement of the forward velocity. Okay, so I mentioned this particular first order formulation because it is the one that you will find used by Christodoulou in his book on three-dimensional fluids from 2007. So in other words, if you wanted to follow along by getting a copy of that book and looking at his discussion, you could do that, and you would find that this is the setup being used. There are some advantages to the setup. One of them is that the entropy is not present in the second equation. Not explicit. There's no derivatives of the entropy in the second equation, which makes some of the calculations a little bit easier. But there's nothing fundamentally important about this particular setup. Here is another one. So instead of using pressure, one uses this variable called h, which I introduced in my work with Descanzi. The h is just the log of the enthalpy. And actually, it's the log of the enthalpy. It's a log of a dimensionless quantity, where formally it's convenient to introduce a constant enthalpy that's positive called h bar. And then you divide the enthalpy by h bar, and you take the log, you call that little h. And then you get a similar looking formulation of the equations. But now you have the derivatives of the entropy appearing in this equation, whereas when you use the pressure, you don't get this extra term. And let me just say that this particular version of the equations for smooth solutions is completely equivalent to the other version, and is easy to work with when you're trying to understand shock waves. So that's the easier to work with, I should say. That's all I want to say about this. This will be this particular formulation in terms of logarithmic enthalpy, entropy, and forward velocity will be important in lecture 3. Okay, so how about the geometries? This is where things start to get more interesting. What is this other metric? So this is the acoustical metric. It is the Lorentzian metric that drives the propagation of sound waves. And if you look in Christodoulou's book, his 2007 monograph, you can basically you can read about this metric. Now, one warning is that different people have a different preference for the overall conformal factor of the acoustical metric. You can basically take this acoustical metric and rescale it by a constant factor or even a scalar function, and you can get something else that you could rightfully call acoustical metric. And as far as I can tell, there's no canonical way to pick the best version that you want to call the acoustical metric. The different rescalings seem to be good for different purposes. To this day, I have not seen any fundamental reason to prefer one of the conformal rescalings over the other. Okay, they seem to be all equally good. It's more of a matter of convenience. What do you want to call the acoustical metric? Okay, so just a little foreshadowing. The most important geometric aspects of the irrotation of the relativistic Euler flow are tied to the acoustical metric G, not the Minkowski metric. So the Minkowski metric is this Lorentzian metric that's just kind of sitting out there from the perspective of the fluid. It's an ambient metric that plays a role in formulating the equations, but it really doesn't have anything useful to do with the fluid flow itself. Okay. Now here's an interesting computation, which is not difficult. If you compute the unit length, if you compute the length of the floor velocity as measured by this acoustical metric, you will get -1, which is the same length that you need to use the fact that it's the floor velocity is length -1 as measured by Minkowski as well. So that's how you do this computation right from this formula. And that's why I chose this normalization. So this is a good normalization precisely because of this. This tells you something. It tells you that U is time-like, okay? And it also, which guarantees you that this vector field is transversal to any null hypersurface or any hypersurface that is null as measured by G. So I'll call that a G null hypersurface. So basically, no matter what you do, no matter what solution regime you're looking in, large data, small data, doesn't matter. U is always time-like and always transversal to any null hypersurface whatsoever. And when you go to understand shock waves and you try to do estimates for the certain components of the fluid on null hypersurfaces, it's very important that the floor velocity is transversal to this null hypersurface, because for transported quantities that are transported by U, any null hypersurface kind of looks like a regular, if you want, space-like hypersurface from the point of view of that transport operator. You're not going to see any degeneracies on a null hypersurface with respect to this transport operator, because the transport operator thinks that it's, just as good as any other Cauchy hypersurface. Okay. Whereas if you're studying wave equations and you're on a null hypersurface, and as many of you know, there are severe degeneracies that come up. You basically lose control over transversal derivatives on null hypersurfaces for wave equations, and the transport operator does not suffer from this degeneracy. Okay. So I should at least throw up some pictures tied to this geometry. This is not really, it's not really essential that one thinks about this picture, but I think it can be helpful for people that have only thought about Einstein equations to think about propagation speeds for fluids. Okay, so take your favorite hyperbolic PDE. Okay, you need some assumptions. I'm going to be very non-technical here. There's a notion of what's called characteristic subset of the tangent space, and this captures the instantaneous propagation directions for the linearized equations. There's a very interesting class of hyperbolic systems that derive from a Lagrangian and have certain technical properties that Christodoulou dubbed regularly hyperbolic. And you can read about this in the Action Principle and Partial Differential Equations book by Christodoulou. And at the end of the day, for any of these regularly hyperbolic PDEs, you can make sense of these characteristic subsets of the tangent space. And as it turns out, relativistic Euler flow does fall under the scope of this book. It is an example of one of Chris Adulla's regularly hyperbolic PDEs. But in order to put it in that framework, you have to introduce yet another of the flow. And I don't think it's a great use of time to do that because we don't really need those results. I'm just trying to give you some insights into where all of this is coming from ultimately. And at the end of the day, it comes from the fact that the relativistic Euler equations are Euler-Lagrange equations for a certain Lagrangian, which I'm not writing down because it would require that other framework. And if anyone is sort of baffling over why all of these geometric structures with all of these good null properties exist, I haven't talked about these properties yet, but I don't have a great explanation for why all of these structures are present, other than to say, ultimately, the theory derives from the Lagrangian. So you can sort of have some hope that such theories have good properties. Okay, so in any case, if you're interested in relativistic Euler, the characteristic subset of the tangent space splits into two pieces, and you can read about these pieces in the Adulla's monograph. There's the sound cone piece, which corresponds to sound waves, and then there's the span of the four velocity, which corresponds to transport phenomena. Okay, and then here's just a picture. The outer cone is just the Minkowski light cone. It's supposed to look like a Minkowski light cone. The inner cone is the sound cone. So this is showing you that in the tangent space picture, the sound cone lives inside the light cone, and this is the tangent space way of saying that sound travels less fast than light, and that's because of our assumption that the speed of sound is less than 1. Here's the four velocity, showing you how it is oriented relative to this bent cone. And then this vertical line is just the Minkowski time axis. This is just meant to orient you to the picture. This is not part of the characteristic subset. This is just sort of showing you how things look. So if you're studying just the fluid problem, you have two kinds of propagation phenomena, one tied to these cones, and then one tied to these tied to the four velocity. If you were coupling to gravity, you would have this other speed. You would have this other speed that you have to deal with. And I can sort of say some tantalizing things in words, which will hint at some of the difficulties in the open problems that I've named. Let's say that you have some result for a fluid, and the only way you know how to prove it is by doing estimates on sound cones. And so that is the case for a lot of things that I know about fluids tied to shock waves. I don't know how to avoid the need to do estimates on sound cones. Okay. Now suppose that you're coupling to gravity now, and you want to do estimates for the gravitational metric, and you know that you're going to have to do estimates on sound cones. So here's the problem. From the perspective of the gravity part of the system, the sound cone looks time-like. It looks time-like. So if you really feel like you have to estimate the gravity on a sound cone, that's not good because we don't have good estimates for gravity on gravitationally time-like hypersurfaces. So basically, if you couple to gravity, I don't know how to do certain key estimates on sound cones for the gravitational metric, because those sound cones are perceived as time-like by the gravitational part of the system. And if you want, that is a big difficulty. Now, amusingly, if you had a theory of like superluminal fluids and you flip these pictures so that the speed of sound was like 100 and the sound cone was way outside of the light cone, that difficulty would not be present. Then if these pictures were flipped, then sound cones from the perspective of space-time would look space-like. And so you could do estimates on those space-like hypersurfaces and everything would work. So it's precisely because sound is slower that makes the problem harder. If you think that there's some kind of singularity that might be happening across the sound cone, then from the perspective of the metric, the space-time gravity metric, it's like a singularity is forming across a time-like hypersurface. And if that sounds like a hard math problem, then, well, it sure seems that way to me. Except when you're in symmetry so that you can reduce everything to transport equations. Then these difficulties become much easier to handle. The real difficulty is doing energy estimates on time-like hypersurfaces for the gravitational part of the system. You can't do that at top order. Okay, so that was just like a foreshadowing of some of the difficulties that I'll say more about at the end of the school. Okay. So given this geometric setup, how can you prove well-posedness? And let me just say that for applications to, let's say, understanding shock waves, the study of the maximal development in situations where singularities might be forming, it's not good enough to have a theory that is adapted to flat sigma constant time slices. The actual geometry of let's say, what happens in a singular solution can be much more complicated, and in particular, having nothing to do with the standard background foliation of Minkowski space by flat inertial slices. Okay, the actual singular set can be much more complicated, and so you need a technique for well-posedness that is not tied to flat slices, if you want. Okay, excuse me. And sort of the basic framework for well-posedness and energy estimates I'm going to outline here is capable of accommodating basically any region whatsoever where in principle such estimates can even be expected to hold. So just for convenience, so you can compare with Christodoulou, let's go back to the PUS formulation of the flow. Again, this is not fundamental, it's just convenient. And let's take a whole bunch of derivatives of the system, which is something that you have to do when you prove well-posedness. You have to get estimates for the first few derivatives at the very least. And let's call some order n derivative of P, U, and S. Let's call them by P dot, U dot, and S dot. Okay, so these dots just sort of schematically denote some high derivative of the solution. And then by differentiating the equations, you can see that these dot quantities, they satisfy what are called the equations of variation. So this is something that you can read about in Christodoulou's action principle book or his fluid shocks book. They satisfy the differentiated equations or equations of variation, if you want. Where the right-hand sides, these F dot, G dot, H dot, and homogeneous terms. By the way, it doesn't even matter so much what you're differentiating with respect to at this level. This schematic structure still holds, whether you're differentiating with coordinate derivatives, lead derivatives. Okay, where these inhomogeneous terms, F dot, G dot, H dot, depend on no more than n derivatives of the original fluid variables. And then there's this J dot term, which you get from differentiating the constraint equations with respect to the dot operator, and then taking one more derivative with respect to the rectangular coordinates. Okay, so basically you can differentiate the constraint and get a certain gain in regularity for this contracted expression. Okay, so these are the kinds of equations that you encounter when you want to prove, let's say, local well-posedness. And then the question becomes, how do you write down energy identities that are useful and maybe adapted to an arbitrarily shaped domain, and that take into account these structures that you find here. Okay. And so here is the method. So this is not literally identical to what's written in Christodoulou's monograph on fluids. This is a slightly modified version that makes it easier for me to talk about. But this, at its core, this is what you'll find in this book. So how do you make a useful energy identity? Well, energy identities are just integrated versions of differential identities. And at the end of the day, all of this is just a divergence theorem. So the easiest thing you can do is to try to write down the vector field J dot, which you will apply the divergence theorem to. And so that is this thing here. And this energy current, as he called it, is a vector field And there are two ways you can look at this. Number one is that you can just kind of write this thing down by hand. You're like, if you're saying I'm looking for energy identities and I want to do divergence theorem, what is the correct thing to write down? And another point of view that one can take is that it's actually the kind of, you can actually derive this existence of this energy current using the techniques from Christa Duluth's action principle book. But that book, the action principle, refers to a different formulation of the equations in terms of what's called the material manifold. And that formulation is really just kind of like a Lagrangian coordinate formulation of the flow. And so if you use that formulation, then you have to translate into this so-called Eulerian picture. And I've never seen that written down. So probably the easiest thing for me to say is that you can just kind of check that this energy current is a good object. Okay. So what is it? It's quadratic in these variations in the dot variables. You can think of this as a quadratic form where the coefficients depend on the solution. And there's like an error term or let's call it a bonus term that's been added on at the end, which is sort of helping you handle the part of the u dot term that is parallel to the forward velocity. Okay, so basically, this vector field will be useful for well-posedness if you pick the scalar function f to be sufficiently large. So you can actually pick it to be a constant. You could take f to be 100 or whatever is the right number for the regime you're in, and everything would work. And then here's the key point, which makes this a useful object for deriving energy identities. If you take the divergence, so this is you can think of this as a covariant divergence, or in coordinates, this is just the usual rectangular coordinate divergence of this current. You will find that whenever derivatives fall on the dot variables, okay, you can use the equations of variation on the previous slide to eliminate and replace with inhomogeneous terms. Okay, and so that's a computation that I don't think there's much value in doing. But anyway, here's what you get. And at the end of the day, the statement is that the divergence of this current depends on the variations, the dot variables, and the inhomogeneous terms, and the derivatives of the coefficients. So the derivatives of like p, the derivatives of f, the derivatives of u, all of these things right here. And so if you're doing divergence theorem, this is the kind of thing you'd have to control in the bulk term, in the space-time integral term, in order to set up the usual iteration procedure to prove well-posedness. Okay, so that's all I really want to say about that. This works for any equation of state. Oh yeah, I'll point out one more thing. So you can see right away that something wicked happens when the speed of sound c goes to 0. Okay, so if you're studying fluid vacuum boundary problems where the speed of sound is going to 0, you can see that this term will become dominant. No matter how you rescale this energy, you could say, I want to get rid of this problem by rescaling and multiplying both sides by c squared, but that doesn't really eliminate the problem, it just hides it. This term will become dominant, the pressure term, and so you're sort of losing control over certain parts of the solution. Okay, and so that's why the problem is hard near a vacuum boundary. And again, we're staying away from that. Okay, and so now about positivity. If it's one thing to write down a quantity whose divergence appears controllable, but if you want to do energy identities and energy estimates, you need positivity. You need to have a coercive energy, otherwise you're not going to get anywhere in the problem. And then here's the statement. And so this is very important. So take the acoustical metric G. So this is not the Minkowski metric, but this is not the spacetime metric. This is the acoustical metric. Take any covector C that is time-like with respect to G, so that this self-inner product is negative. And just so you can pick a sign, so it should be path-directed. And so one way to talk about path-directed in this context is that the inner product of C with respect to the gradient of your flat time function t is negative as measured by the acoustical metric. Okay, and then choose that s parameter to be sufficiently large. It could be a scalar function, it could be a constant, doesn't matter. Then there's a computation that can be done. It's not hard. You will see that this contraction is positive definite in the variations. Okay, positive definite in the variations, and this is sharp. If this were equal to 0, in other words, if c were null, as measured by g, you would not have this. This would be a false statement. That's provably false. This quadratic form would not be coercive. It would be semi-definite, and that's a real effect. And this is not a difficult thing to prove. If you simply go to your favorite, so how do you prove this? One way to do it crudely, pick your favorite space-time point x, and Minkowski rotate the frame, or Minkowski rotate the rectangular coordinate so that at that particular x value, the forward velocity is just this vertical vector. And then the computation for the coercivity it's a straightforward computation based on the Peter-Paul inequality, or however people call it. Okay, so I don't really want to get into those details if they're not particularly interesting at this level. But now you have everything you need. You have like an energy current. Its divergence is controllable in terms of the variations and the inhomogeneous terms. You have positivity when you contract against time-like covectors, and now you're ready to set up your identity. Okay, and so here's the picture. I'm not going to explain every single symbol in this picture because I'm going to only explain the ones that are relevant for this discussion. If we have time later in the school, then I will revisit this picture and say some things about its connection to the study of the boundary of the maximal development for shock forming solutions. Okay, but here's the upshot. So take your favorite picture that looks like this. So this is some space-time domain. M is supposed to be like the solid region. And I've tried to draw things in such a way so that it makes it clear that this domain is not really having any simple connection to the flat rectangular foliations. This is a curved domain if you want. What are the assumptions? That you have a top piece called sigma tilde t, which is space-like with respect to g. That means that its normal n hat in covector form is time-like. So basically n hat is one of these allowable x's from the previous lemma. And similarly, you may think that initial data was given down here on sigma tilde 0, a different space-like hypersurface with its own future directed normals. And then maybe you have a lateral boundary, which I'm calling h bar here. H bar is the lateral boundary, and it could be null with respect to g, or it could be space-like. Null is the borderline case, of course. And so this is the setup. And here, this n bar with a hat over top, this is the normal, the future directed normal to the lateral boundary, h bar. So in other words, if h bar were null with respect to g, then this vector n hat bar would in fact be tangent. So in my picture, the way I've drawn it, this lateral hypersurface is space-like. Okay. And I've been lazy and not written the integration measure normalizations because they're kind of unwieldy to write. So I'm not writing the volume forms, in other words. But basically, anytime you have this picture, and let me just say that these vector fields z and this vector field g bar are not important for the current discussion, so pay no attention to them. Nor are these spheres up here. We can ignore them as well. But for any domain such that this picture holds, you have an energy identity that says that this quantity at time t is equal to the same quantity at time 0. So this is like the energy, which is positive by this slide. Error term, which will also be positive or sorry, this is I didn't explain the sign here. So let me just say that this has the good sign. So this, the way I've written it, it looks like a positive term, but it's actually got the sign such that this term works in your favor. So it's actually, overall term is negative semi-definite. And then the error term is the space-time integral, which is the divergence. And we know from a couple of slides ago that this divergence, you can use the equations of variation, or if you want, use the fluid equations to do substitutions to get error terms that you can control. Okay, so this is the main, once you have this, you can basically prove local well-posedness for the fluid on any domain that looks like this. The only requirement is that this sigma tilde t can't be too far above sigma tilde 0 because a singularity might form. So, you know, let me just say it's pretty much the standard story. You can prove a priori estimates for solutions in L2 base Sobolev spaces on any finite region that looks like this. And of course, it doesn't have to be a finite region. You can extend this to infinite slabs if you want. And you could, using the well-known techniques, you can easily prove well-posedness for initial data in H3. Like take the pressure, velocity, and entropy to be in H3 by using the contraction mapping principle, applying it to the linearized equations. And it's one of the canonical places to read about this kind of argument in our field is certainly Ringström's book on the Cauchy problem and relativity. Of course, he's not treating fluids. He's treating gravity in this book, but the mathematical techniques used here are certainly relevant. Okay, and then later on, maybe in lecture 4, if there is time, I will talk about how these geometric objects that I've been introducing can be used to push this regularity threshold quite a bit below H3, actually. Okay, quite a bit. But I'll save that discussion for later. Okay, so this is like not a bad point for me to stop and see if people have questions. And also maybe David, you can tell me like what is the, or do we take a break after this halfway mark, or what's the?
Yeah, George, thanks a lot. So we can maybe take a small break, also given the fact that for us it's already evening and we might need to just refresh for 5 minutes. But maybe if there are questions, or from here, from the audience online. So let me read the question. So how far can one push the regularity down?
That's a really really nice question. The answer involves splitting the solution into different pieces. And there are different answers one can give, depending on how one splits and what one assumes. So first, let's say let's take irrotational solutions. So irrotational solutions. Then there is work by Kleinerman-Radniansky and Smith-Tataru that say that for irrotational solutions, so irrotational means, again, that the dynamics can be studied by, I'll go all the way back to the beginning. For irrotational solutions, you can basically introduce a potential and study the solution by using wave equation techniques. Okay. And the result ultimately by Smith-Tataru from so I'm going to say around 2005 or 2006, says that for such irrotational initial data, you can go to H2 plus epsilon. So anything above H2. And moreover, results by Lindblad. So I don't think he actually treated the equations of relativistic Euler, but morally he treated equations that have the same qualitative character. Lindblad's work shows you that basically H2 is impossible because of instantaneous shock formation. So really, if you're in the irrotational class, H2 plus epsilon is optimal within the scale of Sobolev spaces. There are people that are interested in like fractional or logarithmic Sobolev regularity. So in other words, H2 plus epsilon there's known well-posedness, but you might be able to play with the logarithms and get something a little bit sharper. That's not really my area of expertise, but it's possible that you might further sharpen this. Now, if you go to solutions with vorticity, then the story becomes much more interesting. And there are results on non-relativistic Euler. There's no result for relativistic Euler yet, but I have a PhD student who's nearly finished such a result on relativistic Euler. If you go to solutions with vorticity, then in the non-relativistic case, I did some work, some collaborators, Descanzi, Mazzone, and Luo, and we split the solution up into like a wave part and a transport part. And the wave part was allowed to be H2 plus F, like in the irrotational case. And the transport part was required to be quite a bit smoother. So we needed the vorticity also to be in H2 plus epsilon. And then we needed some additional Holder regularity on the vorticity. And so something surprising is you can actually propagate that extra regularity for the vorticity, even though it's coupled to the rough wave part. Okay, so we did this a couple of years ago. And then after that, Qian Wang sharpened it. He got rid of the assumption, he basically got rid of the assumption that that you need some Holder regularity on the transport part. So she has a result for non-relativistic compressible Euler that says the sound wave part can be H2 plus epsilon, but the vorticity also has to be H2 plus epsilon. And actually for her, she had two epsilons. There was H2 plus epsilon for the sound wave part, and then H2 plus epsilon prime for the vorticity part, and the epsilon prime was allowed to be smaller than epsilon. So these are the kinds of nuances that people in dispersive PDE arm wrestle over sometimes. And then Qian has a about what the sharp threshold is, but maybe I'll save that for future discussion.